We have therefore seen that if you are going to excite one phase of stator winding with an alternating current, you get a pulsating MMF, which in turn gives a pulsating magnetic field. Now, this is not of much use in electrical machines because it is an oscillating field, and any electromagnetic force that would be generated would exactly become opposite after half a cycle, and you would not have any sustained means to move. We have the other phases as well, and let's see how to make use of the other phases of the machine. So here we see that we had made use of the R phase. We still have the B and G phases that are remaining to be used, and we have already seen that the alternator or the synchronous machine, when linked to the electricity grid, is given supply on all the three phases. So how do we make use of it in the machine? So let's go back to the figure of the machine. So we call the entire set R as one phase. So this is phase R. This entire set is then called as phase G, and this is phase B. Now we know that the electrical supply in the grid is having RYB phases or RGB phases, and we know that the phasors of these phase supplies, that is the R phase, Y and B, are separated by 120 degrees. This is what we call as a balanced grid, where the magnitude of the R phase, magnitude of the Y phase, magnitude of the B phase are all identical, and the phase separation is 120 degrees everywhere. Now here also we have the phases that are there in the machine, R, G and B. They are distributed, but let us see if we have something that is separated by 120 degrees. So here we note that, for example, in this entire machine, in the whole machine that you see here, you have 360 degrees of the circumference, and this 360 degrees of the circumference is divided into 24 slots, which means that the angle between every successive slot is 360 by 24, which is 15 degrees. So that means we are saying that this angle between slot 1 and let us say slot 2 is 15 degrees, slot 2 and slot number 3 is another 15 degrees, and so on. Slot 1 and slot 24 is another 15 degrees. That is the arrangement. Now we said that the location where the maximum value of the MMF of the R phase occurs lies exactly in the middle of the phase of R. That is, you have the phase of R spread out here and here, and the maximum value of the MMF occurs exactly in between. So that's not exactly here as we have drawn it, slightly shifted. So the middle will occur at right in between the slots 8 and 9. Now if you look at the similar arrangement, so let me draw this by a red line so that we know that this is the axis of the R face. Now if you look at where the axis of the other faces are going to lie, suppose we take the B face, you have 9, 10, 11, 12 here, and it occupies 21, 22, 23, 24. Just like you had the middle of this face occurring right in between the green and the blue after the red. So here again you need to look at the middle being right after this. You have the end of the B spread, the spread of the B face, and then you have the next red, and the blue axis would occur exactly here. That is then the midpoint really of the blue face. So we may draw a line corresponding to that axis roughly here, which we can then see what is the angular separation between these two. But let's draw the axis of the green face also before that. So the green face starts over here and then it ends there. This is one spread, and then you have the other set that is there here. So we need to look at here, if you look at the R phase axis, that is 1, 2, 3, 4, 4.5 slots away. So similarly for the blue phase, then after this ends here, you will have 4.5 slots away, 1, 2, 3, 4.5 slot. So that is where the axis of the green phase would then lie. Now if you look at these things, what is the angular separation between these two? This axis, this angle, that angle is then given by the angle between this location and this location on the machine, which is one slot pitch, that is the distance between here and here, 1, 2, 3, 4, 5, 6, 7, and then you have half here and half there, so that is 8 slot displacements. So 15 into 8 is equal to 120 degrees. So that means this angle is equal to 120 degrees. That is, we are saying the axis of the R phase is displaced from the axis of the B phase by an angle of 120 degrees. Each slot is separated from its adjacent slot by an angle of 15 degrees. Right, so you have 8 slot separations here, so that is 15 degrees. Similarly, the angle between these two is, you have half here, so 1, 2, 3, 4, 5, 6, 7, and then another half here and half here, that is 8. Therefore this angle is also 120 degrees. Similarly, you can show that that angle will also be 120 degrees. Now since these axes are separated by 120 degrees and the incoming AC supply from the grid is also having a phase separation of 120 degrees, note that this is the phases in the machine, or the phase windings in the machine are displaced in space by 120 degrees, and we are going to give a supply which is phase shifted with respect to time by 120 degrees. So maybe it's a good idea to link up the phase that is phase shifted with respect to time and give it to a phase in the machine which is space separated by 120 degrees. Let's see what happens if we do that. So we are now looking at giving the R phase supply of the grid to the R phase winding of the machine, and we know that this is going to give rise to a pulsating MMF. We have already seen how that works. In order to have similarity with the machine that we have used, I would like to rename the RYB that is coming from the grid to R B and G. So the B phase supply that is designated from the grid, I am choosing it to designate a phase lag of 120 degrees, and it is the G phase, I am redesignating it, I am giving it the designation which lags this by 240 degrees. So now let us say that we are going to supply the B phase of the grid supply is connected to B phase of the machine. Remember, B phase of the machine, the axis of the B phase of the machine, the winding of the B phase of the machine is space separated from that of the R phase by an angle of 120 degrees here, as we have seen, and we are going to give it a supply that is lagging that of R phase with respect to time by 120 degrees. And what would happen to that? So we now know, as per the understanding that we have developed here during this understanding, so you see that the MMF of R phase and the MMF of the B phase are separated by 120 degrees, and therefore what do you expect will happen? Now let's say that you are going to excite the R phase with an oscillating waveform, with excite the R phase with a sinusoidal waveform, and we saw that it generates an oscillating MMF. Now if you excite the B phase with a sinusoidal waveform, the B phase will also generate an oscillating MMF. The R phase oscillating MMF will oscillate about this axis, whereas the B phase oscillating MMF will oscillate about this axis. If you are going to give the same flow of current to the R and the B phase, then both of them will oscillate together in synchronism with each other. But however, we know that the waveform of the B phase in the grid is phase shifted from that of the R phase by 120 degrees. This phase shift is with respect to time, which therefore means that if you are going to have the flow of let us say that this is I, and you are going to have a flow of current in the R phase which is going to follow a sinusoid, then we know by virtue of the fact that B lags it by 120 degrees, the phase current of B would lag by 120 degrees. It would go something like that. Which means at the instant when the R phase current is 0, Y phase current would be negative. At the instant when the R phase current is maximum, Y has a small negative amplitude. When y is 0, when b is 0, then the R phase has some other one. The instantaneous, the maximum value of the R phase and the B phase are obtained at different instants of time, and therefore we do not expect that the oscillations will happen in synchronism with each other, but these oscillations, there will be oscillations, but the oscillations will be phase shifted with respect to time. So let's take a look at how this oscillation is actually going to look like. Here we see how these oscillations are going to look like. You can see that one waveform leads and the other waveform lags. This, for example, if it leads, then this lags by 120 degrees and the axis is also 120 degree later. So the maximum value of the green phase here is, this green is just to show a difference. Please don't mix it up with the green that we saw on the machine. This is just to show that there are two phases. So you have this phase and the second phase. So the axis of this phase always is here. It reaches the maximum value always at this particular angle. The maximum value of this phase always occurs at this angle. And you can see that these oscillations don't happen in synchronism with each other. There is a phase difference. But nevertheless, one can see that the duration of oscillation, that is how long it is going to take for the cycle to repeat, is the same in the first phase and the second phase. The same amount of duration it is going to take for one phase to repeat itself is the same thing for the other phase as well.